Radiation is a known danger in space, so let me tell a little bit more why it is a big challenge and why it is different from the radiation sources on the ground. So on the ground, we have plenty of, radioactive materials within the nuclear industry and other parties that work with them. However, most of the materials we're using or radioactive waste we have to deal with emit alpha, beta, gamma radiation and neutrons. However, the energy of those particles is not that high. What do I mean? What does it mean exactly? It means that the shielding for alpha can be very thin, and beta radiation sources like cesium or strontium can be also uh, defended against with relatively thin shielding. Of course, gamma is more penetrating, but heavier metals can be used to shield against that, and water is a very good shielding against all sources of radiation. The second thing is the sources themselves are usually fixed in one location, be it nuclear power station or spent fuel pools, and it's relatively easy to build the shielding as thick as you need. On submarines, there are also quite a lot of mass available for the shielding, and water around them provides additional protection. In space, things are considerably different. Radiation is everywhere, and while it is pretty much the same type, like charged beta protons and electrons, gamma and neutrons from the sun, the energies of those particles is much higher, can be orders of magnitude higher, and therefore they penetrate the shielding a lot deeper, and we need a lot more thicker shielding to protect against them. Additionally, high energy beta creates secondary radiation that can make actually things worse if you use any kind of heavy metals for the shielding. And big problem is mass budget is very limited for any spacecraft or space station. Every gram matters, and we cannot spend a lot of that on building meters of shielding as we can do on our planet. However, things are actually not as bad, meaning that we can design the shielding against radiation in space that's thick enough to remove any immediate danger. It will, however, present some additional health risks. So if you look at the chart, you can see the four major lines, and the topmost one is radiation exposure for a human in the relatively thin shielded spacecraft like Apollo during the solar flare. They will get a radiation dosage of over lethal threshold over 5 sieverts, so 500 rams, and that absolutely will kill you, and your death will not be pleasant. However, at the same time, with just a little bit of heavier shielding, think radiation shelter inside the bigger spacecraft, the dosage for the solar flare will be reduced to the much lower one that will not present immediate danger to your health. It will, however, present an additional risk of cancer and other potential health impacts, but not immediate ones. That's for the solar flares. Now for the other major source of radiation, which is the constant background, it's actually not that high, and you don't need like a heavy shielding to reduce it. However, it's very difficult to reduce the constant galactic background to the level that's the same for the low Earth orbit. You can see the difference in shielding, that 3 orders of magnitude more shielding only reduces it by so much. Water and aluminum can be used for this type of protection, and if combined together, our spacecraft crew on the trip to Mars, as well as any orbital colonists, will be defended against the immediate dangers of acute radiation sickness. However, they have to find a way to deal with the long-term effects of increased radiation. So the short answer, we can absolutely reduce the radiation, so it will not be an immediate death threat to our Martian colonists. However, it will be additional risk factor for anyone visiting Mars or anyone living there full time.